We know that from Faraday's law, the voltage EMF is equal to minus n, the number of turns multiplied by the flux change over the time, d flux over dt. The variation of flux with time may be caused in three ways. The first way is to have a stationary loop in a time-varying magnetic field. The second way, time-varying loop area in a static magnetic field. And the third way is to have a time-varying loop area in a time-varying magnetic field. The EMF voltage can also be written as in terms of electric field and magnetic field. The voltage EMF is equal to the closed line integral for the electric field, and it's also equal to the negative derivative of the surface integral for the magnetic field with respect to time. Now first, the stationary loop in a time-varying magnetic field, and it's also called the transformer EMF. The voltage EMF generated by this way is called the transformer EMF. So if we have a stationary loop like this, as an example, let's make it as a circle, and we have a resistor that is connected in this stationary loop. And here we have the magnetic field that goes across the stationary loop, denoted by B. And this magnetic field is varying magnetic field. So what will happen is that there is a voltage called the EMF voltage. In this case it is called the transformer EMF, that will create a current, and that current creates a magnetic field in the opposite direction of the original magnetic field. In order to try stopping the magnetic field, the applied magnetic field, and retain the magnetic field is equal to 0 across the stationary loop. So using the right hand rule, we want to create a current that creates a magnetic field in the opposite direction of the applied magnetic field in order to try and stop this magnetic field. So first, let's assume that the current direction is in this direction. Now using the right hand rule to determine the direction of the created magnetic field, the thumb will be in the direction of our current assumption, and the other four fingers will be the direction for the created magnetic field. So that means using the right hand rule for this direction of the currents, we get that the magnetic field is in this direction. As you can see here, the created magnetic field for our assumption current is in the same direction for the applied magnetic field. So our assumption is wrong, and the direction of the current, the induced current, will be in the opposite direction. So now the same thing, we assume that the current is in this direction, and using also the right hand rule, the thumb with the direction of the current, our assumption direction of the current I, and the rest of the fingers is in the direction of the magnetic field, indicates the direction of the created magnetic field. So using the right hand rule, we get that the magnetic field direction is like this. As you can see here, the created magnetic field is in the opposite direction of the applied magnetic field, so our current assumption for the direction is correct. And because the direction of the current is in this direction, we get also the induced EMF, the induced voltage EMF across the resistor. So here we get the voltage EMF across this resistor, and it is called the transformer EMF in our case. Now, as we said earlier, that the voltage EMF is equal to the voltage EMF across this resistor will be equal to, using the Faraday's law in the integral form, the closed line integral for the electric field is equal to the negative of the derivative of the surface integral for the magnetic field with respect to time. Now let's apply Stokes theorem for this formula. The closed line integral will now be surface integral for the curl for the electric field dot ds is equal to, so we can integrate the derivative inside the integration, and we get minus surface integration partial magnetic field with respect to time dot ds. Now because here we have both surface integral and ds, so we can remove the surface integral and we only left with the inside. the curl of the electric field is equal to minus the partial for the magnetic field with respect to time. So we end up with this formula, and this formula is one of the Maxwell's equations for time varying fields. We get this Maxwell equation for our case, stationary loop in a time varying magnetic field.